Can A group fails? This is the question. So the first one is, what is the problem with the boundary of African plates surrounded by the ridges? This is the African plate and the ridge surrounding. And the African plate is with no associated with subduction. So the ridge beside it is all spreading. And so it will move south, west, and east. And the plate still grows in size, so it's expanding. And the mid-Atlantic ridge is westward, which is this one. This is mid-Atlantic ridge, and now it's westward. And the Indian ridge is eastward. So the second question is, what does the mantle melt? Why does the mantle melt and upwell at the ocean ridge? So the picture here shows the mantle upwelling, and this is the passive upwelling. So first the plate will spreading like this. And then the mantle will rise up from here to fill the gap. And the mantle rise up here, and will form new crust. And this upwelling will only happen in a shallow part of the mantle. And it's caused by the plate spreading itself. And this will only happen on the uppermost mantle, very shallow. And the third question is, why does the plate subduction take place? And this is the subduction, the plate, and the rock here will, because here the pressure is higher, and the higher pressure will make the mineral denser. So the density will increase in here, and from 3.0 gram per centimeters cubic centimeter. And now you will increase here to 3.3, and this density increase to 3.6. And the density higher here will drag the subduction plate downward. So cause the plate subduction. So the final question is, does the plate geometry correspond to mantle convection cells? The mantle convection cells means it's like the mantle moving under the plate. And the sentence from the textbook says it did correspond, but the relationship is complicated. In the ideal thinking is the convection cells is regular, but actually the mantle cannot consist a regular size. And before I talk the passive upwelling, it might happen in other places, because the convection cells will not be a regular size. And the upwelling and downwelling cannot happen in the same place. And there can be no regular pattern of convection cells. So this is the end of my talk.
A group. Yes.
In the very beginning, you talk about African plate, and you say it will go west, go east, go south. And my question is that why it didn't go north? In your content, page 4, fall.
Oh. This is only in my opinion, because there is no size from here to gold node, I guess.
No what? Sorry.
No space. I only read from the textbook, so it only say from south and west and east. Although it's all surrounded by the reef.
More A group student. Any? Okay, yeah.
And in the very last, you talk about tranquility, and the rock will rolling down and down. And why makes the density of rock become heavier?
You mean what?
The density became heavier. Why?
Why? Because the pressure, as you go more deep, as you go deeper, the pressure here is become higher, so it will squeeze the mineral and make the density increase. Okay.
A group student. Any student? Question from you. I see. Okay, Vincent.
As you just mentioned, the rock will go down and its density will increase. It's because the pressure increase, right? But my question is, as the pressure increase, the size of the rock must, because of the pressure, it will decrease. Then the total weight may be the same.
Yes.
So why it have a power to pull the plate down?
It's not because of the gravity dragging it down, it's because the density higher here will. Buoyance. The buoyancy rate will. Or maybe it's because the mental density. Okay, I said it wrong. Okay. The mental. This is the 3.3 is the mental density. So after the density increase, if the density for a mineral in the subduction zone is higher than the mental density, so it will sink.
Jackie.
Want to answer different in rock, different mineral have their own melting point, right? So I want to know if the pressure go higher and temperature is go higher too, and what if some of the mineral in the rock melting first? What will happen to this density?
My answer will only be, from my knowledge now, is the subduction zone will finally melting, but I think it won't influence the downward of the subduction zone. So if some of the minerals start to melt from here, it just become part of the metal.
Any more questions? Okay.
Same thing. And first, does this phenomena happen frequently in I mean, this phenomenon is always happen in a conjunction plate or divergent plate, and why?
You understand?
I think it only happen in a is it conjunction?
Convergent.
Oh, convergent. Okay. It only happen in the convergent. I think the divergent plate will be this one, and this will only let me think a little. And because convergent place is two forces squeezed together, but this I think subduction zone is a little different from the convergent because it's only I think there's no force here, it's only subduction zone dragging itself down to the mantle. So I cannot tell whether will it happen frequently in convergent zone, but it won't happen in divergent zone. Okay.
Okay. It's correct that convergent zone and subduction zone, they are different concepts, but the difference lies at convergent zone means two plates crush together, and in some cases subduction takes place, but in other cases there's no subduction because the two plates that crush into each other might have similar density. In that case, mountain building will happen, 造山运动. So I think that's what you mean, right? Okay, so my question, can you go back to the slides of the African plate? Is it correct that you said the African plate is surrounded by only ocean beach? Is that what you meant?
Sorry, only by reach.
Only by reach. Okay. Then what's this? What's this boundary? We heard that there are many earthquakes in Italy. There are also many volcanoes in Italy. So what kind of plate boundary is it?
This place is convergent.
Right. Okay, I was thinking that was a convergent zone. So in the Mediterranean Sea, 地中海, there is a very large subduction zone going on there. This one. Okay. Then my next, can you go to slide number 5? So this is the text of my question, right? Okay. Why does mantle melt and upwell at the ocean ridge? And can you go to your answer? Okay. And my question actually corresponds to Jackie's question. Jackie asked, you don't need to go there. He was asking, when a plate subduct, then the mineral should encounter higher temperature, so they should theoretically melt. And in this case, this mantle material here, because this is a plate and this is mantle, it upwell, and the temperature should be lower. So why should it melt? So in other words, it's a little bit counterintuitive. Here, the material goes upward and it melts. Why?
It melts because the pressure decreased here and the the melting point decrease.
What's the specific term for the melting point? That's what we learned 2 weeks ago. Just 2 weeks ago. A very complicated phase diagram with 2 minerals.
It decrease the
Not liquidus.
you take it.
No, not you. Just remember the key terms. Anyone? What Stella said was right. So the material melt here. Actually, what I was asking with this question is, if you think clearly, this is counterintuitive because when a material moves upward to the crust, the temperature is lower, and when temperature is lower, usually you don't see material melting. But in this case, you actually see the mantle becomes magma and flows out of the ocean ridge. So my question is, why can this happen? And this actually links to the concepts I introduced 2 weeks ago. So, under what circumstances will rock actually melt on Earth? And she said, it is because of the decrease of pressure. But why should decrease in pressure results in the melting of rocks? And then she mentioned because of a lower melting point. Well, this is also correct, but there's another term to describe the lower melting point. What's the specific term for the melting point of multiple mineral, like a 2-mineral system or multiple mineral system? What's the term? Anyone? What's the term? All right. The term is solidus. Solidus. Okay? So solidus is actually the same as melting point, but it's a more exact term to describe a multiple mineral system, because we know in mantle there will be multiple minerals. And melting point is usually for a single material. Okay. So if you can answer this question, then can you go to slide number 7? And can you answer Jackie's question again? Why should we expect the material to melt easily when the slab or when the plate subduct?
No. Why? Because the pressure increase here.
And the pressure increase, so
The solidus will also increase.
right,
It's hard to melt.
exactly. So why can't we see the slab melt easily? So why didn't we see that? Because the pressure increased. So you have to combine this question and the knowledge you learned 2 weeks ago. What really controls rock melting on Earth is not the temperature gradient, but the pressure gradient. So usually you see rock melting only when it moves upward, and you do not see rock melting when it moves downward. All right. Okay. Thank you, Alice.
First, talk about the sauce.
Anna, please speak louder.
The first talk about
Isostasis.
isostasis.
Right.
The fluid will flow and adjust until the pressure in the Earth's surface rise or falls in response to a change in load. The ocean and continentals reflect those states and static adjustment require a mental flow. In the A diagram, the square bars refer to the metal and the rectangle blocks refer to the crust. And here, in this diagram, it confirms that the metal cannot flow, so the crust is just on the crust just on the metal with different thickness and different density. And in the B diagram, it shows that the metal can flow and the crust just flow in the metal with the same density, different thickness. And we see it is more thick if of condensation is deeper. And C diagram, the metal is controlled to the crust in the flow in the metal with the same thickness, different density. And the density is bigger, the depth of condensation is bigger as well. This is post-glacial recount. During the glacial period, ice was in added load and coast condensing, while post-glacial period, the ice started melting and the continent able to rise. In the A diagram, this glacial ice is at added load on the crust, so the crust became sinking, the mantle move away. In this diagram, the ice started melting, the load become lighter, the crust rising until come in. And C is that the crust is become balanced. Here is the static found in the Hudson Bay. The number bigger than 0 is means that the crust in here is rising, and lower than 0 is here's crust is sinking.
How about the other diagram? The right one, right.
I think it is how much it rises.
What about the black line and the gray line?
The black line is for each one spot.
Where is it?
In here.
Alright.
And this is breathing city is right here, and it's sinking. The convection is depend on the magnitude of the density and normalized the viscosity of the material and the distance involved. A random number with the term that enhances convection in the numerator and notes that included is in the denominator. The alpha is coefficient thermal expansion, G is gravitational constant, T is temperature, H is distance, the eta is viscosity, the kappa is thermal conductivity. For the mental viscosity is large, and its temperature and distance is large as well. And it may the random number is based for the mental is basically the threshold for convection. The mental convection is inevitable. And in this rough diagram, I think is the ideal diagram about how mental convection. And in this diagram is maybe is how the mental convection in real life. While the random number becomes bigger, the convection will much less organized. The large scale convection drive the motion of tectonic plates to the small scale convection is mostly occurring in the uppermost mantle by increment of spreading open of the vertical plate. So the ocean ridge is like the upwelling thing of the mantle convection.
All right. D group, question. Do you all agree? D group. No question? 质疑
So, may I ask what is the exactly geological feature in the for the mental convection patterns?
What's your question again?
What is the exactly geological feature to the upwelling peak of the mental convection?
Jing asked, can you repeat again? What is the exact geological feature that corresponds to the upwelling limb of a convection zone, of a mental convection cell? The upwelling. Mental convection, and what's the upwelling limb? What kind of geological feature does it that correspond to the upwelling part?
The ocean, the ridge is correspond to the upwelling limb.
Do you agree?
I have another answer.
Alright,
But I don't know. I have another answer, but I don't know if it's correct or not. In my opinion, I think it will happen hotspot, new ocean crust.
hotspot, new
Yes.
ocean crust.
Hotspot of new ocean crust.
Hotspot or new ocean crust. Alright, so Jing said she think the upwelling part of a mental convection cell does not correspond to mid-ocean ridge, but to a feature called hot spot. I wonder how much B group student have this answer because this is what is now generally accepted in geoscience community, that this is wrong. This is wrong. So that's the most important concept for this class. Unfortunately, during my past few years, even after my repeated emphasis of this key concept at the final oral exam, the student who happen to have this question, they always say, oh, the upwelling limb is ocean ridge. Well, this is so deeply rooted in your brain by high school geoscience education that you always think, okay, this is the convection cell is like this, and this part is mid-ocean ridge. Unfortunately, this is not right. And I will tell you more evidence later during my lecture, but this is unfortunately wrong. So if you read the textbook, it will tell you what geologists believe that is the upwelling lake is hotspot, or in another term is called mantle plume. Okay, let's see. Can you exit? Exit and. Okay. More big group student, more question. Okay, Ethan.
What is the red light number called according to the ice? What is the relation about to this?
To what?
Red light number and to the ice.
You mean the post-glacial rebound?
What's the
Okay, is there what's the relationship between your slide 3? Yes, post-glacial rebound and red line number.
I didn't think that they were related.
Do you have your own answer, or that's a pure question?
So why do we need to know the post glacial rebound? Because we know there's a force under the
Under what?
this under the
Don't Chinese? Under what?
under the plate.
Plate. Under the plate.
Yeah, and this is going to be I don't know how to say, but I know there's a relation. Yeah, and the next week.
All right. Later on I will elaborate, but I think what Ethan mentioned is, you go here. So it seems like for the B group student, I just gave you many different keywords, but actually there is some logical link between them. And but probably it's not easy for you to figure out what's the exact logical link. So first I asked about isostasy. But isostasy is a concept for buoyancy study. But we have no way to go to mantle and see if the material there is really dark type, 塑性, dark type. And post-glacial rebound is actually a direct evidence that because after the removal of ice, you see the crust or the plate bounce back slowly. Actually, sorry, the figure here, this should be year before present, but it was missing in the figure. But you see that over time, the height of the Richardson Gulf, the height increased, while at this city, the height decreased. So what has happened? I think you should have learned this in Yongbin's class. So what happened is after the removal of the ice, the crust moves like this. So before it's like this, and then afterward it's like this. It a little bit bounced back. Therefore, this is at the margin. This city is at the margin of this bounce back. So that's the reason it sinks a little bit during the rebound. And then that tells you the mantle is dark type, 塑性的. And therefore, to understand how ductile it is, you can go to Rayleigh number. You can use this equation to do some theoretical calculation because you have no way to observe the whole mantle. So that's what you can do. And you do this with computer modeling. And actually with all the parameters here, there's always a way to obtain some estimate. Like a temperature, distance, thermal conductivity, viscosity. It's possible to know based on limited material from mantle that what might be the value here. And then with all these parameters collected, you can calculate the RA, the Rayleigh number. And what's the Rayleigh number of mantle? Do you have an idea? Do you remember the number? Roughly. It's 1, 100, 1,000.
Over 2,000. Over 2,000. But more bigger than that.
Right. It's at least higher than, she said, at least higher than 2,000, but much bigger, right? If I remember clearly, it's 1 million. Okay. So that's a Rayleigh number of mantle. And the number she mentioned, 2,000, is actually a threshold above which convection will happen. So if the value is above 2,000, there should be convection, but the convection might be regular. Can you go to this one? Might be relatively, you have this nice convection cell. If the value gets even higher, then in oceanography we said there's turbulence. And then you see this irregular, like in a boiling pot, a pot of boiling water, you will see very chaotic convection cells, and that's like that. And this is based on computer modeling, I have to emphasize again. But I think this will enhance your impression what kind of mobility mantle has. This one, between this and this might be the real state of mantle. Okay, I have one last question. Can you go to the first slide? Okay, can you display? Display. Right. Yes, Chris. Okay, we have 3 models here. Which one better explain the condition on Earth? These 3.
There's no way is this one refers to how Earth can move across time.
So you mentioned that the crust all of them have the same density. The continental crust and also the oceanic crust, they all have the same density. So how do you think?
It's like B and C combined together is power is like this.
That's a good answer. She said combining B and C. So this one actually better explained if you consider both continental crust and oceanic crust, because continental crust has a density of about 2.65, and oceanic crust is a little bit heavier. Then you will expect that because of its heavier, higher density, it will sink deeper into the mantle. However, if you consider all the continents, they have relatively same density, but their thickness vary a lot. And actually, this model also tells you an important concept. On the continent, the place where you see high mountains, like this is high mountain and might be the coastal plain, 海岸平原, for example. The place with high mountain also have a deep root. In other words, it's a little bit like iceberg. For iceberg, you see just the top, but below the sea level, you didn't see the rest 90%. The same also applies to the mountain. Therefore, we always say the mountain has a root, and the more the mountain is eroded, the higher it will grow. Okay? Because of isostasis. 就是一座山它那个越侵蚀会长越高。Alright, it sounds weird, but this is because of isostasis. Okay, so Anna, thank you.